Good evening to one and all. Last class we have been discussing about the Gala skills, right? So when we concluded, we ended up with discussing about finite fields and the reason why we are going for finite fields. This is also called as Gala skill, which stands for the general expression of Gala skill of p power n. And we ended up by substituting value of p to be 2 because, as I said, we will be using ones and zeros alone, which will be used in our modern day cryptographic techniques. Wherever we go, we are going to discuss based upon bits, right? Ones and zeros. That's why we are going to discuss only about realized field of 2 power n, thereby using n bit number of words. To understand this thing, that is, if you want to do binary operations like your addition, multiplication, and subtraction, or any binary bits, so we need to do via polynomial arithmetic. So if we move into this polynomial arithmetic, yesterday we just saw Gauss field of 2 power 2. We have 4 elements totally, and each element made up of 2 bits. Right, and you can able to see only zeros and ones alone will be present in all the bits. So to understand this one, we have to go into polynomial arithmetic. So what is this polynomial arithmetic in the sense? It will be represented using a variable called x, which will be risen to degrees from 0 to n minus 1. So n minus 1 denotes the highest degree and the lowest degree is 0. Similarly, you'll be having your coefficient starting from a n minus 1 to a naught. Okay. So based on this polynomial arithmetic only, we are going to represent the binary bits, and this polynomial arithmetic will be put into the mathematical operation, and the final output will be again reconstruct towards your binary bits. Okay. How many of you came across this polynomial arithmetic in your school days or in your lower math? Can you raise your hands? Polynomial arithmetic is solution of a power x and goes on. How many of you have come across this one? Polynomial arithmetic? No, no one. Okay, good. So if you move into this one, directly I'll jump into the representation of bits in terms of polynomial arithmetic. So assume that you have 8-bit word. That is, you're having 8 bits like 1, 0, 0, 1, 1, 0, 0, 1. Right. So this 8-bit can be represented in the polynomial like this. So here the value of n is 8, so which says the highest degree will be. That is the highest degree of polynomial represented by this 8-bit word will be n minus 1. So in this case, n minus 1 is 7 because you are going with 8-bit word. So I'll be starting with x power 7 as highest degree of a polynomial up to x power 0, and the respective coefficient of these polynomials will be the binary values. So here 1 x power 7, 0 x power 6, 0 x power 5, 1 x power 4, 1 x cubed, 0 x squared, 0 x squared, and 1 x power 0. So the first level of simplification, what we do in sense, we'll be omitting all the 0 coefficient values. So in this example, we are omitting these 0 coefficient values, thereby ending up with 1 x power 7, 1 x power 4, 1 x cube, and 1 x power 0. And instead of writing this ones continuously, we can remove this ones and simply write them as x power 7 to x power 4 plus x cube plus 1. So this is how we can able to represent this 8-bit word into a polynomial game. Right. How many of you understood this part of converting an 8-bit word into a polynomial? Can you raise your hands? Thank you, Venkat. Thank you, Arun. Okay. So anyone have any doubt or any confusion regarding this, you are most welcome to ask. If you have any doubt, you can ask me now. Because this is a very basic thing, if people have to be clear with to understand the higher end cryptography techniques, much more.
Right. So for decrypting it, we'll have to simplify whatever the given equation is and then use this.
Yes, yes. Suppose if you are given, if you get your polynomial arithmetic directly, means you have to re-expand to this n-bit word. We'll see in the upcoming slide. Like what you're asking is like this, right? Suppose they ask you find me the 8-bit word, and if you're given polynomial is x power 5 plus x squared plus x. So here they said that it is an 8-bit word, that is n is 8, So obviously it makes the highest degree of polynomial, that is n minus 1, to be 7. So I have to first expand this given polynomial with respect to missing degrees. So if I expand this polynomial, I'll be getting from 0 to x power 7 to 0 x power 0. Then you can directly write the coefficients alone as a binary value. I hope this is the point you are asking, right?
Yes,
So
sir.
suppose, so there is a trivial question for you, sir. Why you are taking this 8-bit only as an example? Can anyone tell? 8-bit makes how many bytes? Why we are specifically concentrating on this 8 bits alone? Why can't we go for 7 bits or 9 bits kind of? Can anyone tell? 8-bit makes how many bytes?
1 byte, sir.
1.
Yeah. Since everything is going to be in terms of bytes, right? And we are going to discuss with each and every frame with 8 bits. That's why we are just taking the examples in terms of 80. Right. Now we move on to the polynomial arithmetic operations. Right. So here we can able to perform two operations, that is operation based on the coefficients and operations on two polynomials. So here two polynomials are two different polynomials. Like you have your this is one polynomial. Like assume this is your f of x means I can create another polynomial with g of x and we can able to do perform some operations between these two polynomials. Operations are coefficient in the sense since we are discussing the Galois field of 2 power n, our coefficients will be 0 and 1 alone. So nothing much to have discussion on this one. So we'll directly jump into operations on two polynomials. At that moment, we'll be discussing how these zeros and ones can be dealt in the polynomial arithmetic operation. Right. We'll go with the ordinary polynomial arithmetic. Because from your school days, how you people are doing your polynomial arithmetic, like addition, subtraction, everything, as well as multiplication. So assume that you have your two polynomials like f of x and g of x. So f of x is x cubed plus x square plus 2, and g of x is nothing but x square minus x plus 1. Right. Now they ask you to add these two polynomials. So if you add, obviously you're going to get x cubed. So we have 2x square, so 2x square minus x. Then if you add this 2 with the 1, I'll be getting 3. Right. And f of x minus g of x, obviously we'll be getting x cubed x plus 1. Right. Because f of x minus g of x means all the signs will be still minus, plus and minus. Then accordingly we'll do the operation. And multiplication, you can able to see if you multiply these two. So here the powers will be added here. So x power 5, 3x square minus 2x plus 2. So these are the basic polynomial arithmetic which we study from your basic school math. Right. It's a basic polynomial math. I hope you people are clear with your basic math, right? Regarding this polynomial arithmetic. If anyone have any doubt in this basic polynomial arithmetic, you can ask me. If it is clear, raise your hands. If you have any doubts, you can ask. Regarding the basic polynomial. Yeah. Now we move on to polynomial arithmetic, where I'm going to introduce the modulus part. So what is the need of this modulus part? From the previous slide, the example we just saw, we are going to add two polynomials. And while adding these two polynomials, the resultant polynomial which we got does not create any polynomial which is moving out of a set. So what do we mean is out of a set in the sense? One second, I guess what is if you take these two polynomials, I'm going to add these two. The highest degree of this polynomial among these two is x power 3. The highest degree is 3. So after adding these two polynomials, the resultant polynomial highest degree is also 3. It is not exceeding this 3. So if you get x power 2 also, it is okay because it is within the set. Get x power 1 also, it's okay. But if you are getting x power 4, x power 5 and all, means moving out of set. Since your highest degree is itself 3, which will move or greater than 3. So doing addition of polynomials or subtraction, we are not going to create any polynomial which is going to move out of the set. But this is not the case when you perform multiplication. Because if you multiply two polynomials, it may create, and here you have to listen to this carefully, there are possibilities in it. It may create a polynomial which may go out of a set which will be a degree greater than n minus 1. You can see the same example here. Here n minus 1 is equal to 3. N minus 1 is highest degree, which is equal to 3, highest degree. Whereas if you multiply this two, I'm ending up with a degree which is x power 5. So x power 5 is greater than x power 3. So therefore it is moving out of set. Like, assume that you are manipulating 2 bytes. So you'll be having 8-bit word as a one polynomial. Assume this you have fx. And you'll be having another 8-bit as your g of x. If you multiply this one, you'll be going somewhat higher degree. Assume that you are getting like x power 9. Instead of 8 bits, you'll be getting 10 bit, means there is no use. With the 10 bit, you can't able to create a byte. So you have to reduce it. So, but as I said, if you are going for multiplication, we are going to move away from the degree. So in order to bring it within the limit of n minus 1, we are going to introduce the modulus part. So if you remember in our module 1, when we are discussing classical encryption techniques, we use this modular operation with respect to 26 because we are using English as alphabet, English as a language. So we'll be having 26 alphabets. So we don't want the resultant number to go beyond 26. So we use this modulus part. The same way in polynomial also we are going to use a modulus part, but here the modulo operator will be called as an irreducible polynomial. So for each and every degree, we have a set of polynomials called irreducible polynomials, and these polynomials will be prime polynomial. Prime means as a prime number, it will be divisible by itself and one alone. Right. So using this irreducible polynomial only, I'm going to reduce or I'm going to bring the out of set values within the set. Right. So have you got the point of why we are going for this modulus part in the polynomial? If you get the point, raise your hand. Still, sir, I'm not clear why we are going for this one. You can ask me. Okay. Thank you, Sandeep.
So can you explain it once again?
Okay. Shall I go to directly example so that you get a clear picture of it?
Okay, sir.
So these are irreducible polynomials for each and every degree. That is, when n minus 1 is equal to 1, these two polynomials will be used. Like this, for each and every degree, we have set of polynomials. In examination, we'll be providing any one of the polynomial for your numericals. So don't worry, no need to remember these polynomials. We'll be providing the irreducible polynomial. And before going into that, this point is the most important point you people have to remember before going into this modulus part. So whenever your polynomial arithmetic is coming into picture with respect to cryptography is concerned, here both your addition and subtraction operation will be treated as the same operation. That is, whenever your addition or subtraction comes into picture, I'll be using it as a XOR operation. This point is the most important point. Whenever addition or subtraction comes, I'll be using it as an XOR operation. We'll see an example here. So here they're asking you to multiply these two polynomials, x power 5 plus x squared plus x cubed plus x squared plus 1 under Galois field of 2 power 8. So here the value of n is 8. So the highest degree will be n minus 1. So it should be 7. The first step, so here it is going to be addition here, right? Here I'm going to add. So addition, first step, what we have to do is we have to expand this to polynomial. So if I'm expanding this polynomial, you can able to see, since highest degree is 7, I'm filling with the missing coefficients here. So 0 x power 7, 0 x power 6, 1 x power 5 because I have x power 5 here, 0 x power 4, 0 x cube, I have x square, so 1 x square, 1 x power 1, I have here, and 0 x power 0. Similarly here x cube, so from x power 7 to x power 4, you can able to see here, from x power 7 to x power 4, all 0 coefficients, then x cube, x square, 0 x power 1 and 1 x power 6. But here, whenever I say addition, as I said, we are going to perform XOR operation. So here, 0 and 1 will be 1, 1, 0 will be 1. Here you can able to see. We go with the conventional polynomial arithmetic, we will be writing as 2x square. But in, from cryptographic point of view, since we are going to perform XOR operation, 1x square will be resulting in 0x square. So here 1x cube, 0, 1, 0, and 0. Now to omit all the 0 coefficients, I'll be ending up with x power 5 plus x cube plus x plus 1. And here you can able to see the resultant highest degree is 5. So it is well within degree of 7. So there is no issue here in respect to addition is concerned. Arun, I'll just come to your multiplication part in the next slide. So people just understood this addition part with respect to XOR operation. Can you raise your hand? Because in multiplication, we'll see the usage of this polynomial, irreducible polynomial. Okay. Actually, there's also another shortcut. Like directly, I can able to convert them into binary values. Then I can able to XOR these two binary values to get the answers also. Right. Next comes the multiplication. So here, whenever a coefficient multiplication is done in Gauss-Miller tool, so if you are multiplying any two x values, x power I plus x power j, will be ending up with xi, x power I plus j. So this may create, as I said, it may create. Sometimes it may not, sometimes it may. Whereas if you go for addition, it won't create a partial. But for multiplication, there are possibilities of creating a term which has a degree more than your n minus 1 value. So at this moment, we will be using an irreducible polynomial to cut short the result. We'll see how it goes. So we'll take an example here. And here we have said that find the result of these two polynomial under multiplication. And here the multiplication will also be represented like this. Again, under Java is equal to 2 power 8. If the n is equal to 8, so your highest degree is n minus 1 is 7. And here they given you, this is the irreducible polynomial you should use whenever you are going to exceed your highest degree. So highest degree is 7 means the degree of operation is 8 because your n is 8. So able to see here. Degree is based on n values. Right. So in this case, if the highest degree is n equal to 8 means I'll be using the irreducible polynomial with highest degree of 8. Right. Now we'll see how this is going to happen. What they did in the sense, we are no need to expand the operation how we used to do in the addition. I mean, in addition, so directly what they did in the sense, they multiply. So x power 5 is multiplied here, x square and x from the first polynomial. So if you multiply this x power 5 with this one, what I am getting, you can able to see, I'll be getting x power 12 because it's x power 5 plus 7 is 12, 9, 8, 7, and 6. So with this, I have performed this first multiplication. Next, if you go with the second part, that is your x square part, I'll be getting x power 9, x power 6, 5, because my multiplying x square by cube, I'll be getting x power 5. Right. Now, if you multiply this again, this x square, I'll be getting x power 4, again x square with x, I'll be getting x cube. But this part is right. Right. Next, if you go with the final part, that is where you multiply your x to this one. So I'll be getting x power 8, x power 5, 4, 3, and 2. So this last part is over here. Right. Now I'm going to add the polynomials of similar power. So x power 12, I'm just checking. I don't have anything here, so x power 12. X power 9. So as I said, we are going to use only XOR operation whenever the addition comes into picture. So if you in XOR, if you're using both the bit as same number, will be resulting with 0. So x power 9 and x power 9 gets cancelled. 8 and 8 gets cancelled. 7, we don't have a x power 7 anywhere. So I'll be using x power 7 directly here. X power 6, x power 6, and x power 5, yeah, we have 2 x power 5. X power 5, x power 5, x4, x4, and x cube is also getting cancelled. At last, we'll be ending up with x square. Okay. Now, see the final resultant value. Here, the highest degree ran for 12. So, till this step, how many of you are clear with this one? Till this step, how many of you are clear? Can you raise your hand? Yeah. So, the facing issue, because the final resultant which we found is found to be highest degree of 12, but we should get only highest degree maximum of n minus 1, which is 7, right? So n minus 1 is 7. So we have to reduce this highest degree of 12 to come below n minus 1, which is 7. So for this, I am going to take a modulus of this polynomial with respect to this irreducible polynomial. So how we are going to do this one? So I take this is the final result which we got, and this is the irreducible polynomial. Simply divide this by. So highest degree is 8. Here is this 12. So I'll be multiplying with x power 4. So x power 4, if it is multiplied with this one, I'll be getting x power 12, 8, 7, 5, and 4. Now, if here generally in division will be subtracted. As I said in cryptography, whenever addition or subtraction comes into picture, we'll be using an XOR operation. So again, here if you XOR, x power 4 gets cancelled, I'll be getting x power 8, 7, 7 gets cancelled, simple 5, 4, and 2. Now this goes one times, x power 8, 4, 3, this one. This gets cancelled, x power 4 gets cancelled. At last, I'll be getting that as x power 5, x cube plus x square plus x plus 1. So here you can able to see this value, the highest degree is x power 5, which is less than my highest degree, which is to be there for Gala scale of 2 power 8. Highest degree should be 8, sorry, 7. So here at last we got it to be 5. Thereby the answer is x power 5 plus x cube plus x square plus x plus 1. So these things, this modulus part will be coming into picture only when the highest degree is greater than 7. Even if it is equal to 7, we will stop with that part. Is it clear, guys? This part? Yeah, I hope Arun, you got the point, right?
Yes, sir.
Anyone have any doubt in this one? Okay. Now we move on to the inverse, multiplicative inverse. I hope you people will remember our extended Euclid algorithm. Like if you have a integer called b and you have a modulo operator for n, how will you find the multiplicative inverse of b under the particular modulo operator here? So here, if you assume this is the value of p and this is the value of n, so we'll be initializing this one as r1 and this one as r2, and we'll be coming our Euclidean algorithm. Okay, where you will be finding the multiplicative inverse. So here you can able to see how this works. So here R1 is taken, R2 is taken, and the value of T1 will be initialized to 0 as we already discussed. T2 will take value of 1. So now I'm going to divide this one with this one. So I'll be getting a quotient as x squared plus 1 and the remainder to be x. So how will you compute the T here? T is T1 minus 2 times T2. Here the T1 value is 0 and minus Q is x squared plus 1 and your T2 is again 1. So here the final answer should be minus of x square plus 1. But if you see here, they're writing it as plus x square plus 1. Can anyone tell why there is minus of front of? Any guess? So we're discussing polynomial arithmetic under cryptography. So why this minus sign is not there? I gave a clue. Even if we move to the second step, assume it is, it is actually this is correct. X square plus 1. Next step, they push this R2 to R1, R came to R2 place. Here one came here and this one came here. So in this case, if you divide this one, goes with the quotient of x and the remainder of 1. So now second step, the value of t will be t1. T1 is 1 minus q times, that is x times t2 x square plus 1. So if you expand this one, 1 minus x cubed minus x, but here they written it as x cubed plus x plus 1. All the minus signs I will change to plus. Any yes, anything? Again, this is also correct only, what they written. Okay, I will just tell the answer. So as I said, in polynomial arithmetic with respect to cryptography is concerned, all addition and your subtractions altogether are going to be used as a as a XOR operation. Okay. Here all the negative signs will be used as addition sign only, because if you are going to manipulate anything for addition or subtraction, will be obviously going to do with XOR. So nothing to do with your minus sign here. That's why they will pick all the positive values. And that is, if you are subtracting this, it means that you are XORing this two. Right? You are XORing this two. If you XOR means while solving, you're getting at x cube plus x, then plus 1 will be final result here. Right. So if you try for this one also, last step you'll be getting the output. And at last, once they found the when R2 runs for 0, this is the GCD. So once your GCD is once, then 1, then obviously I'll be getting a multiplicative inverse, and this is the multiplicative inverse for this polynomial under this modular operation. How many of you understood this part of finding multiplicative inverse in polynomial arithmetic? This is worthy for 10 marks, guys. So I want you people to be clear with this part. If you're clear, kindly raise your hand. If you have doubt, you can ask me. If you have any doubts, you can. And I think it is like clear that I want you people to solve this one. It's very simple here. Last day to find like multiplicative inverse of x power 5 in this model. So as of now, I want you people to tell me the value of t for the first iteration, and second iteration. Once you find the value of t in the first iteration, post in the chat box. After that, you can proceed in the second iteration. And this is value of this is n and this is b, and you'll be taking this one as R1 and this will be an R2. So you'll be dividing R1 by R2. The first one will be easily you can able to tell me the answer for t. So you can use your chat box to tell me the value of t for the first iteration. Once you finish the first iteration, then you can go for the second iteration. If people facing any difficulties, kindly notify me. I'll help you. First step you can easily find, because obviously you're going to get your quotient to be x cube. From this you can directly tell the answer for it. I need at least one response, then only I can able to proceed. Yes, Arun. Have you found the
Should
answer?
will be x raised to 5 for T2.
No, tell me the answer for first equation. Then you can get that. Your T1 will be 0 and T2 will be 1 for first equation. Using this T1, T2 value and the quotient cube, tell me the answer for this one. Then
X cube, sir. First one.
the first one is x cube. Yes, correct.
Yes, sir.
Tell for second equation.
Doing, sir.
Okay, sir. Okay, sir.
Sir, x power 4 plus x cube.
Okay, Sandeep. Yeah, I will show the answer for rest of the thing. Actually, x power 4 plus x cube plus 1 will come. I think you would
Yes,
have
sir.
this.
Plus one also, sir. Yes.
Yeah. So this is how you'll be doing your extended equilibrium algorithm. Okay, for finding the inverse. I hope now you people are okay with this polynomial part, right? If it is clear, kindly raise your hand so that I'll move on to the next topic.
So can you tell us the calculation once?
calculation of which one? The entire process or second step?
Sir, I got T1 T
Okay. I
first
mean,
T.
you got first T, you got, okay, second T.
Wait,
What is the answer you got? You just tell me and I'll tell you where you went wrong.
sir, I didn't get 1x raised to power 4x. Sir, I'm just a little confused with the process. Can you tell us just
Okay.
quickly?
Okay. So, I mean, you are clear with the first process, right? First is the first iteration. I mean, this T calculation, you are clear, right?
Yes, sir.
After this, I'll be pushing this R2 to R1. This R will be coming and sitting in the place of R2. And T2 will be pushed to T1 and the value of T is pushed to T2, right? So in the second step, if you divide this x power 5 with respect to this one, simply what I will do in the sense, okay, if I have this x power 5, and I'm going to divide this with x power 4 plus x cube plus x plus 1. First step, I'll be going with simply x. So I'll be getting x power 5 plus x power 4 plus x square plus x. So this will get cancelled. Next, I'll be left with x power 4 x square plus x, right? Again, I'll be going with plus 1. If you do, I'll be getting a remainder as x cube plus x square plus 1 because this x power 4 would have been cancelled. This part you're clear, right? You're getting this portion. Understand?
Yes, sir.
Okay. So now I got my T1 to be 1 and T2 to be, x cube. So we once again look at this part. So in this one, if you compute the value of T, T1 is 1 minus Q times, that is x plus 1, Q times your T2, that is x cube. Right. So here 1 minus x power 4, this will be 125 x power 4 plus x cube. Right. So this minus will be, if you convert them into plus, we'll be getting x power 4 plus x power 3 plus 1. I hope you get the point. Yeah. Is it clear,
Yes,
Evan?
sir.
You just try these two steps, okay, in home leisurely. If you face any difficulties, we will discuss it in the next class also. Okay. After like 3 classes, I'll be giving a practice problems also for all these things for you people to work out. Is it okay?
Yes, sir.
So with this, we are concluding this polynomial arithmetic. Now we are moving to the next one called prime numbers, because to understand these theorems based on our syllabus, we have this Fermat theorem and Euler's theorem. To understand this one, we should know what even by prime numbers. How many of you know what even by prime number? Can you raise your hand? Simplest question ever. If you people say you don't know me, that's all. What is the prime number? Well, then I can skip to the introduction part. Smallest prime numbers are understand. So this thing, one trivial fact I want to reveal here. I'm asking list the prime numbers less than 10. So less than 10, I have 4 prime numbers, 2, 3, 5, and 7. So if you list the prime numbers less than 15, you'll be getting 2, 3, 5, 7, 11, and 13. So out of 10, I got 4 prime numbers. Here out of 15, I got 6 prime numbers. Right. So here it roughly occupies 40%. Right. Of this one. And here you can able to see how much it occupied out of this one. Here the 40% is it roughly comes to 60%, roughly closer. So not 50%, less than 50%, so around 30% comes. So here the point what they want to say in a sense, if you increase the range, okay, range in the sense where up to 10 or 100 and goes on, increase the range, the percentage of prime numbers will be keep on decreasing. When the range increases, the percentage of prime numbers will decrease. Right. For example, I'm giving you a number called n, any integer, and asking you to find whether the given number is a prime number or not. How will you find? Any method you know? Okay, if you learn from your school math, if so, you can share it in the chat box. I hope I'm audible. Any method you know, if you can know? Guys, have you learned the highest common factor kind of things and that before I explain the process?
So to find HCF.
Yeah, those things the people would have used, right?
Yes, sir.
Now, another easiest way, but it is an inefficient way, is how we can able to find difference by finding the root of a particular given integer. Okay, if you have that number, take the square root of that number. Okay, and here find the numbers which are less than the particular root. For example, I just tell you. For example, suppose I am giving you the number called 97 and asking you to tell me whether it's 97 is a prime number or not. The first way what I will do is I will take the root of this one, so that it can come to closest to this one. It's not nothing but either 9 or 10, because 9 square is 81 and 10 square is 100. So this is the closest number to 97. You can choose any one according to yourself. And this number which you are going to choose is called a floor value. Floor value of 0, I mean, square root of 97 is 9 here. And I will be choosing the prime numbers less than the particular floor value. And I will check whether these prime numbers can able to divide the given integer. If it is divisible, then it is not a prime. If it is not divisible, then the particular number is a prime. So in this case, 97 is a prime number. That is, if you given any number, take a square root and find which number is closer to this one, like 9 square or 10 square or 8 square is closer to this particular number, and choose that particular number as a floor value, and choose the prime numbers less than that particular floor number, and you can able to choose it. Right. So how many of you understood this part? You can raise your hand. Or if it is not clear, means you can ask me. Whether 301 is a prime number or not. First, can you people tell me what is the floor number you are going to choose for this one? That is, if you square any integer, okay, should be closer to this 301. Which integer will be choosing? Okay, 16. You are choosing 16. Okay. So prime numbers less than 16 are 2, 3, 5, 7, 11, and 13. So you have to check whether this C01 is divisible by any one of these prime numbers. If you check 2, obviously won't, because it's not an even number. 3, if you add this one, you get 4, so 3, 1, 4, 1, 2. 5, obviously not, because C01 it will be either ending with 0 or 5, so 5 is not divisible. Check with 7 whether it is divisible by 7 or not. 301.
No, sir. Yes, sir.
Divisible, sir.
Divisible.
Yes, sir.
So 7 is dividing 301, means then 301 is not a prime number. Here I have chosen 17 as a floor value. You can choose 17 or 16, whatever you wish, but you will see this will be like this. So here 7 divides 301, so 301 is not a prime number. So it's the simplest way, okay, to find this prime number. This is called a C of Eratosthenes, that is, it has all the prime numbers up to 100, and here they are striking this 4, but it's not visible. So with this, we'll wrap up today's session, because all the theorems which are going to discuss after this one,